Voyager 1 is already farther from Earth than any other human-made object, moving through interstellar space on a trajectory set decades ago. One day, its final instrument will fall silent, its last signal will fade, and the spacecraft will continue without us as the galaxy slowly changes around it. In about 40,000 years, it will pass within roughly 1.7 light-years of Gliese 445. But even that encounter is only the beginning of a journey that could continue for trillions of years. So tonight, the question is simple. If Voyager 1 keeps drifting long after Earth, the Sun, and almost everything familiar has changed, where could it be 10 trillion years from now? Before we begin tonight's journey, subscribe if you want more calm space documentaries like this. Leave a like if you enjoy deep space mysteries. And here is a question. If Voyager 1 could carry one final message from humanity into the far future, what would you want it to say? Let me know in the comments. I will pin the most thoughtful answer. Tonight, you are watching the Just About Space channel, talking about where will Voyager 1 be in 10 trillion years. Voyager 1 is already living in a part of space where almost nothing made by humans has ever gone, traveling outward through the thin material between the stars, while the solar system continues shrinking behind it. The spacecraft was launched in 1977 for a mission that once seemed ambitious enough, simply because it would cross the outer planets. Yet the strange thing about Voyager is that its most extraordinary journey began after the famous encounters were over. Jupiter and Saturn became memories. The familiar architecture of the solar system fell away, and the probe continued into a region where there was no destination waiting for it, and no plan to stop. Even now, while Voyager still speaks to Earth, every signal is a reminder of how far that journey has already gone. Commands take many hours to reach the spacecraft, and its replies require the same long return, so the people operating it are never seeing Voyager as it is in the present moment. They are always working with a delayed version of the spacecraft, listening to information that began crossing space long before it reaches an antenna on Earth. That delay will continue growing as Voyager moves farther away, turning communication into an increasingly slow exchange between a small machine and the planet that built it. Engineers have already had to choose which instruments and systems deserve the remaining energy, shutting down equipment that once played a major role in the mission so that more important functions can continue. This means the end of Voyager will probably not arrive as one dramatic instant when the spacecraft suddenly dies, but as a gradual narrowing of what it is still able to do. One instrument stops operating, then another. Heaters receive less power, systems are managed more carefully, and eventually the probe becomes too weak to keep sending useful science back across the enormous distance. One day, that will change, and the final signal may not announce itself as final when it arrives. Engineers could receive another set of data, another routine transmission, or another weak carrier tone, and only later discover that nothing else is coming. They may attempt commands, adjust antennas, wait for the correct timing, and search for any trace that the spacecraft is still able to respond. Because a loss of contact does not always mean the spacecraft itself has stopped functioning completely. A transmitter could fail, a power system could fall below the level needed for communication, or Voyager could simply become too faint for Earth to hear reliably. If that moment comes gradually, there may never be a single clean second that can be marked as the exact instant Voyager 1 became silent forever. Instead, the distance between successful contacts may grow until operators understand that the conversation is over, and the spacecraft that spent decades reporting from the edge of human reach will continue without anyone receiving its story. The silence would belong to us, not to Voyager, because nothing about losing contact automatically stops its motion through space. That distinction is what makes the far future of Voyager so strange. Most machines become irrelevant when they stop working because their purpose depends on someone using them. But Voyager will continue obeying the same laws of motion, whether its transmitter is active or completely cold. Its engines are not driving it through interstellar space in the way a car drives down a road. The spacecraft already has momentum, and there is almost nothing in the surrounding environment capable of slowing it quickly. Once communication ends, the mission as a scientific conversation may be over, but the physical journey continues. The probe would become a dark, silent object, carrying no active instructions from Earth and receiving none, while still moving through the galaxy at tens of thousands of kilometers per hour relative to the Sun. Its antennas would no longer be useful as a bridge home. Instruments would eventually stop returning measurements, and electrical systems would fall silent, one after another. Yet the body of the spacecraft would remain. The high-gain antenna, the old instrument housings, the booms, the metal framework, and the golden record would continue traveling together, even when none of them serves the purpose for which it was originally built. This transformation from spacecraft to artifact is difficult to define, because it happens in stages. Voyager may still retain some electrical activity after meaningful science has ended, or some components may remain warmer than the surrounding environment long after communication is lost. But eventually, those distinctions stop mattering from a human perspective. There will be no one nearby to inspect it, and no maintenance crew to replace an aging circuit. The spacecraft simply becomes an object drifting through interstellar space, carrying evidence of a civilization that once knew exactly where it was. 1,000 years after the final signal, Voyager would still be close to the beginning of its journey by galactic standards. It may have traveled an extraordinary distance compared with anything humans can currently reach. Yet even thousands of years barely move the spacecraft across the space between stars. This is one of the important shifts in scale, because what feels unimaginably long to a civilization can be almost insignificant to the galaxy. Voyager does not need to hurry. It has no deadline, no crew aging inside it, no fuel schedule for arrival, and no destination demanding that it reach a certain place. 10,000 years would carry it much farther, but even that is still only the opening stretch of what the spacecraft could experience if it survives. By then, everything connected with the active mission would belong to deep human history, and the Sun itself would be only one star among many behind the probe. The path would no longer be described meaningfully by distances measured from Earth, because Earth would have moved around the Sun billions of times. The Sun would have moved through the galaxy, and the nearby stars would have shifted relative to one another as they followed their own orbits. Voyager's famous direction in the sky is therefore not a promise that it is traveling toward a fixed point. Stars are moving too, and the galaxy is not a static backdrop painted behind the spacecraft. Every nearby star has its own velocity. Every stellar neighborhood changes gradually, and the Sun itself is circling the center of the Milky Way. So the geometry that seems simple when viewed on a modern star chart becomes increasingly different as thousands of years pass. Voyager is not heading through a frozen map. It is moving through a galaxy in motion. This is why the first known close stellar encounter in Voyager 1's future is so useful. Not because the spacecraft is actually going to visit another star, but because it gives the journey its first recognizable marker after communication ends. Roughly 40,000 years from now, Voyager 1 is expected to pass within about 1.7 light-years of the star Gliese 445. That sounds close only because normal interstellar distances are so large. A separation of 1.7 light-years is still an enormous gulf, far beyond anything that would resemble a planetary flyby or a meaningful arrival. By then, the spacecraft will have spent far more time drifting silently than it ever spent communicating with Earth, and the civilization that launched it may have changed beyond recognition, or may no longer exist at all. The golden record will still contain greetings, music, images, natural sounds, and information chosen to represent Earth in the 20th century, but the people and places recorded on it will belong to an unimaginably distant past. If some future observer somehow found Voyager then, the spacecraft would not describe the world that currently exists. It would describe the world from which it originally departed. For a while, those calculations can remain extremely useful because the positions and motions of nearby stars are measured well enough to estimate future encounters. Yet every prediction becomes harder as the timescale expands. The farther into the future we ask about Voyager, the more the problem stops being a simple extension of its present velocity and becomes a question about the gravitational environment of the galaxy itself. Passing stars can alter trajectories slightly. The Milky Way continues evolving, and tiny uncertainties that are irrelevant over decades can grow into much larger differences over millions or billions of years. None of this means Voyager suddenly begins wandering unpredictably in the near future. For many thousands of years, its path can still be described with meaningful confidence, which is why encounters such as the passage near Gliese 445 can be estimated. The important point is that 10 trillion years is so far beyond this regime that the precision suggested by a modern map becomes meaningless. Before we can ask where Voyager will be at that distant time, we have to understand how quickly the familiar reference points around it begin disappearing. Microscopic dust grains could strike the spacecraft at high relative speeds. Cosmic radiation would continue passing through its materials, and thermal conditions would remain extremely different from anything experienced by ordinary machines on Earth. Most of the time, nothing dramatic would happen, which is precisely why Voyager can plausibly survive as an object for extraordinary periods. But survival is not the same as remaining unchanged. Paint, coatings, electronics, exposed surfaces, and delicate components do not need to remain functional for the spacecraft to continue drifting as a recognizable artifact. The Golden Record has a different kind of importance because it was deliberately protected for long survival. Mounted beneath a cover intended to shield it from some of the environment around it. Whether it could remain readable after fantastically long times is much harder to guarantee, but the intention behind it becomes more striking once Voyager is silent. The record was never necessary for the spacecraft to complete its scientific mission. It was included because the people who built Voyager understood that the machine might continue long after its instruments stopped working, and wanted something about Earth to travel with it. As 40,000 years approach, the Sun and Gliese 445 will both have moved substantially from where they appear today. And Voyager's encounter will happen because all three trajectories happen to bring the spacecraft and star into the same broad region at the same time. There will be no braking burn, no orbit insertion, and no change in mission status, because there is no mission left to control. Voyager will simply pass through the star's distant neighborhood and continue onward, carrying whatever remains of the spacecraft into another stretch of darkness. That passage is a useful reminder that interstellar travel without a destination is almost impossible to think about in human terms. We normally understand journeys through departure and arrival, but Voyager's future has only departure. There is no station at the end, no planned world where the spacecraft is expected to stop, and no point at which its path becomes complete. Every encounter is temporary. Every star is something it passes rather than reaches, and every milestone leads into another span of time much larger than the one before it. 40,000 years sounds like the deep future because it is longer than the entire period of recorded human civilization many times over. Yet compared with 10 trillion years, it is almost nothing. If the full lifetime we are about to follow were compressed into a single year, Voyager's encounter with Gliese 445 would happen within roughly the first fraction of a second. The spacecraft would still have essentially all of its unimaginable future ahead of it. And once Voyager 1 has passed the first recognizable star on its silent journey, the scale of the story begins to change completely. Because tens of thousands of years are only the opening steps into a future where even the stars around it will no longer stay the same. By the time the spacecraft has moved beyond its distant encounter with Gliese 445, almost everything that once made its journey easy to describe will have become less useful. Earth will no longer be a practical reference point. The constellations familiar to people today will have been reshaped by stellar motion, and the Sun itself will have traveled a noticeable distance along its orbit through the Milky Way. Voyager will still be moving through space, but the map around it will no longer resemble the sky from which the mission was launched, because stars that appear fixed over a human lifetime are only temporarily arranged that way. Every star in the galaxy has its own motion, and although those motions are usually far too slow to notice from one generation to the next, tens of thousands of years are long enough for the pattern to begin changing visibly. Some stars drift closer together from our point of view. Others separate, and familiar constellations lose the shapes humans gave them because their members were never physically attached in the first place. Voyager would move through this changing geometry without recognizing any of it, carrying a star map on the golden record that described the neighborhood of the Sun as it existed near the end of the 20th century. For Voyager itself, none of this creates confusion because the spacecraft does not navigate toward a target anymore. There is no onboard plan that says which star should come after Gliese 445, no correction burn scheduled for the distant future, and no computer waiting for a new destination from Earth. Its trajectory simply continues under gravity, carrying it through a moving population of stars, while the galaxy slowly determines which objects will pass near it and which will remain impossibly far away. The word near becomes especially misleading on these timescales, because even a close stellar encounter can leave Voyager separated from a star by distances that would require years for light to cross. A spacecraft, moving at Voyager's speed, could spend tens of thousands of years approaching the broad neighborhood of a star and then continue onward without ever passing through anything that resembles a planetary system. The galaxy contains an enormous amount of empty space, and Voyager is so small that even after traveling for ages, it is far more likely to cross darkness than to strike a world, a star, or another large object. The journey after Gliese 445 would therefore be dominated not by dramatic encounters, but by long intervals during which almost nothing happens from a human point of view. A nearby star slowly brightens over thousands of years, reaches a closest approach while still remaining far away, then fades behind as the spacecraft continues onward. Another stellar system may pass at a different angle much later, followed by another stretch of darkness so long that entire civilizations could rise and disappear during what amounts to one quiet segment of Voyager's path. That creates a strange contrast with the spacecraft's beginning, when every movement was monitored carefully and each planetary encounter produced images that millions of people could see. During the Jupiter and Saturn flybys, Voyager was a machine surrounded by attention, receiving commands and returning discoveries that transformed our understanding of the outer solar system. Tens of thousands of years later, the same object may still exist but attract no signal, no photograph, and perhaps no memory at all, even though physically it has never stopped moving. The Sun would continue moving too, which means Voyager is not simply escaping from a stationary point left behind at the center of its past. Our star travels around the Milky Way, along with the rest of the solar system, carrying the planets through the galaxy, while Voyager follows a different path created by the velocity it gained during its planetary encounters. Over enough time, the distance between the probe and the Sun becomes part of a larger orbital problem, where both objects are responding to the gravitational field of the galaxy rather than one remaining fixed, while the other travels away. This matters because the phrase, "Where will Voyager be?" eventually has no useful answer unless we also ask, relative to what? Relative to Earth, the answer changes as Earth circles the Sun and the Sun crosses the galaxy. Relative to the center of the Milky Way, Voyager follows one long path, while the solar system follows another. Relative to nearby stars, its position changes again as each star follows its own motion. On short timescales, we can choose Earth or the Sun as an obvious reference. But in the deep future, those coordinates become less intuitive because everything we are using as a landmark is moving too. Even the Milky Way is not a rigid structure. Stars orbit through it at different speeds and directions. Clouds of gas shift, stellar groups disperse, and gravitational interactions slowly rearrange local neighborhoods. Voyager is too small to influence any of this, but it is carried through the same changing gravitational environment, which means that a simple line drawn outward from the solar system cannot describe its path forever. The line is useful for imagining the opening part of the journey, while the real future becomes a curve shaped by the galaxy and by encounters that are impossible to predict perfectly over immense spans of time. For the first tens of thousands of years, those complications remain manageable enough that astronomers can estimate particular stellar flybys, because the current positions and motions of nearby stars are known with impressive precision. As the prediction moves farther into the future, however, tiny uncertainties begin to matter more, and the list of objects influencing the spacecraft becomes larger. A star passing somewhat closer than expected could alter the probe's motion by a small amount, and that small difference can become significant after another million years of travel. This does not turn the future into complete chaos immediately, but it changes the kind of answer science can honestly provide. We can talk confidently about broad behavior and about some relatively near-term encounters, while becoming more cautious about exact positions as the timescale grows. Voyager will remain within the gravitational environment of the Milky Way for a very long time, unless some later interaction changes that outcome. Yet specifying a precise point for the spacecraft, billions or trillions of years ahead, would imply a certainty the available information cannot support. The first 40,000 years, therefore, serve as a bridge between two very different kinds of prediction. Near the present, Voyager's motion is still connected directly to measurements taken from Earth, and its future can be extended using a well-known trajectory through a familiar stellar neighborhood. Beyond that, the neighborhood itself begins changing enough that the spacecraft has to be understood as one tiny moving object among hundreds of billions of others, each following paths that interact through gravity over timescales far longer than any human observation. But there is no reason to expect another civilization to find it, and the more realistic image is far quieter. Voyager passes through the broad neighborhood of Gliese 445, receives nothing, sends nothing, and continues into another region of the galaxy where no destination has been chosen. The star gradually falls behind, the distance grows again, and whatever brief meaning humans attach to that encounter disappears into a journey that does not distinguish between important milestones and empty space. Another 10,000 years pass, then another, and the distinction between one century and the next becomes irrelevant to the spacecraft. Human beings organize time around lifetimes, generations, and historical eras, while Voyager has no internal clock that needs to matter once its power is gone. 50,000 years and 100,000 years are simply different positions along the same motion, and the farther the journey extends, the less useful ordinary human units feel for describing what remains ahead. At around 100,000 years, Voyager would still be only at the beginning of a future measured against the lifetime of the galaxy. Even if the spacecraft had traveled several light-years farther, the Milky Way would remain immense around it, with its disk spanning tens of thousands of light-years and containing stars whose motions slowly reshape the environment. The probe would not be crossing the galaxy in any meaningful sense. It would still be wandering through one tiny part of a structure so large that human history disappears almost completely inside the times required to traverse it. This is where the story starts leaving the scale of individual stellar encounters behind. Because once hundreds of thousands of years accumulate, the question is no longer which single star Voyager passes near, but how its entire stellar neighborhood changes around it. Some stars that are close to the Sun today will move far away. Others will enter the region, and the geometry of nearby space will be rebuilt repeatedly as the galaxy evolves. The recognizable sky of the 21st century becomes only one temporary arrangement among countless others. Voyager itself would become increasingly difficult to connect with any one star, because it belongs to none of them. It was born in the solar system but escaped it, and every later encounter remains temporary unless an extraordinarily unlikely gravitational interaction changes its path enough to capture it. Most likely, the probe continues as a free interstellar object, moving through changing stellar neighborhoods without ever becoming part of a new planetary system. The longer we follow it, the more the story becomes less about engineering and more about the changing universe through which the engineering artifact happens to move. Gliese 445 is only one temporary landmark, and the Sun is only one moving point behind it, while the galaxy begins to reveal itself as a dynamic environment whose stars are constantly rearranging the map. And as Voyager 1 drifts from tens of thousands of years into hundreds of thousands, and then toward its first million years alone, the stars around it stop behaving like fixed destinations and begin becoming part of a moving galactic landscape that will reshape the spacecraft's path again and again. A million years is long enough for the idea of Voyager's present location to lose almost all of its ordinary meaning, because the stars that currently define its neighborhood will have moved far from the places where we see them today, while other stars that are now distant will have entered the same broad region of the Milky Way. The spacecraft would still be traveling under the influence of gravity, but the simple picture of a probe moving outward from the Sun into a static field of stars would be gone. What remains is a tiny object following one path through a galaxy where every surrounding object is following another. On this scale, even the Sun's position becomes part of the story, rather than a fixed point behind Voyager. Our star moves continuously around the center of the Milky Way, carrying Earth and the rest of the solar system with it, while Voyager follows a different trajectory that began with the speed and direction it gained during its encounters with the outer planets. After a million years, both the Sun and the spacecraft will have traveled a noticeable distance through the galaxy, and the straight line that seems to connect them today will have become only one temporary relationship between two moving objects. The Milky Way itself is so large that a million years still represents only a small fraction of the time required for the Sun to complete one orbit around the galactic center. Yet this is already long enough for the local stellar environment to be rebuilt. Nearby stars do not remain neighbors forever, and groups that appear close together in the sky slowly separate as their individual motions carry them along different paths. A future observer standing on Earth, if Earth is still inhabited, would look up at constellations that bear almost no resemblance to the familiar shapes used today, because the sky would have been rearranged by motion rather than by any sudden event. Voyager would be part of that same motion, but unlike a star, it carries almost no mass and produces no meaningful gravity of its own, so it simply responds to the environment around it. Passing stars could bend its path slightly, while the broad gravitational field of the galaxy continues influencing its motion over much longer periods. Most encounters would be extremely distant by human standards, but a small change in direction produced over a million years can matter because there is so much time for that change to accumulate. This is one of the reasons predicting Voyager's exact position becomes increasingly difficult as the timeline expands. The uncertainty does not come from the spacecraft behaving randomly, because its motion still follows the laws of physics, but from the fact that a perfect prediction would require perfect knowledge of the positions, velocities, and future gravitational interactions of an enormous number of objects. Even tiny measurement errors that are irrelevant over a few decades can grow into much larger differences when those same calculations are extended over hundreds of thousands or millions of years. For relatively near stellar encounters, astronomers can still calculate meaningful estimates because modern observations give us precise information about the motion of many nearby stars. But the farther the prediction is pushed, the more each small uncertainty has time to influence the result. A star that passes slightly closer than expected can bend Voyager's path by a little more, which changes where another encounter happens later, and the differences continue accumulating. The spacecraft does not become unpredictable all at once. Our confidence simply becomes broader and less exact. Whether humanity would still exist in anything like its current form is impossible to know. And the same uncertainty applies to languages, nations, technologies, and even the meaning future beings might give to the word human. Yet none of that changes the basic physical fact that the spacecraft could still be there, because Voyager does not require a civilization to remember it in order to continue moving. The object can outlast the story attached to it, drifting through the galaxy, even if every archive describing its purpose has been lost. That possibility makes the golden record stranger on a million-year timescale, because it would still be carrying a deliberate description of a world from 1977, while Earth itself continues changing. The continents would have shifted slightly, species would have evolved or disappeared, climates would have changed, and any civilization remaining on the planet could be separated from the makers of the record by a cultural distance, impossible to estimate. The sounds and images preserved aboard Voyager would no longer represent a recent home. They would represent an ancient version of Earth. The physical record may not remain perfectly preserved, because a million years of radiation, microscopic impacts, and exposure can damage any material. Yet the chance that at least some recognizable parts of the spacecraft survive remains much easier to imagine than the survival of its electronics. The active machine would be gone, but the structure could still persist as a damaged artifact, with the broad shape of Voyager and some of its components remaining identifiable, even after delicate surfaces and exposed materials have changed. Most of its journey during that million years would still be spent in deep emptiness. The average distance between stars is so enormous compared with the size of a spacecraft that even a million years of travel does not make a collision with a star or planet likely. Voyager can pass through regions filled with stars on astronomical maps, while physically remaining separated from almost everything by vast distances, which means its future would be dominated by absence rather than by constant encounters. A million years after launch, Voyager may still be traveling at roughly the same general interstellar speed it carried out of the solar system, although repeated gravitational influences could alter its direction gradually. There is no engine making corrections, no control system deciding which path is preferable, and no fuel reserve waiting for a future maneuver. Gravity alone continues writing the trajectory, while every passing object adds its small contribution to a path no engineer could have designed in complete detail. The sun would still be recognizable at this stage of the story, but it would no longer be the bright central object that defines Voyager's surroundings. From the spacecraft's location, our star would appear as one more distant point among countless others, and its exact brightness would depend on how far the probe has wandered relative to it. The idea that Voyager once began beside Earth would be encoded only in its motion and in the message attached to its body. The surrounding sky would offer no obvious visual sign of where the journey started. The spacecraft has already crossed from the timescale of missions into the timescale of species, and the next jumps will carry it beyond that into the timescale of planets and stars. 1 million years can erase almost every detail of human history while barely changing the sun, which reveals just how large the gap is between the clocks used by civilizations and the clocks used by astrophysics. Voyager is uniquely suited to connect those scales because the same object can survive while the meaning of time around it changes completely. At 10 million years, the local stellar neighborhood would have been rearranged many times over, and the exact chain of gravitational encounters becomes harder to reconstruct from present-day measurements. Stars that are near Voyager then may not be stars that are even considered nearby today, while the Sun itself would continue traveling through different parts of the galactic disk. The spacecraft remains within the broad gravitational structure of the Milky Way, but the simple language of leaving the solar system no longer describes what matters about its motion. 100 million years stretches the comparison even further, approaching the scale on which the Sun makes a substantial fraction of an orbit around the Milky Way. Earth would have experienced enormous geological change during that period, while entire branches of life could have evolved, spread, and disappeared. Voyager, if it survives, would still be moving somewhere within the same galaxy. But any attempt to connect its position to the star map used at launch would be like trying to navigate a modern city using a map drawn before the city existed. Eventually, the Sun will complete another galactic orbit, carrying the solar system around the Milky Way, while Voyager follows its own route through the same immense structure. Whether their paths bring them relatively closer again or carry them farther apart depends on the complicated details of their galactic motion. But there is no simple reason to expect the probe to remain on a steadily increasing straight-line distance from the Sun forever. Both are orbiting within the same gravitational system, and over enough time, their separation becomes part of a much larger dance. This is an important correction to the common image of Voyager, simply flying away into infinite darkness in one unchanging direction. On a small diagram of the solar system, the spacecraft appears to be moving outward along a clean line, which is perfectly useful for understanding its current escape from the planets. On the scale of millions and hundreds of millions of years, however, the Milky Way becomes the dominant structure, and Voyager's trajectory has to be understood as one orbiting path among many inside the galaxy. Passing stars could occasionally modify that orbit, and a sufficiently close encounter might alter the spacecraft's speed or direction more noticeably, although the probability of a dramatic event remains low. Most stellar flybys would simply add tiny changes that become meaningful only after a great deal of time. The galaxy would gradually erase the simplicity of Voyager's original trajectory, not by stopping the spacecraft, but by folding its motion into the much larger gravitational history of the Milky Way. By then, the concept of a destination has disappeared almost completely. A star encountered after 10 million years is no more final than Gliese 445 was after 40,000, and another encountered after 100 million years would be equally temporary. Voyager belongs to no new system unless an extremely unusual interaction captures it. So, the most likely future remains one of continuous wandering through stellar neighborhoods that appear, change, and disappear around it. This is where the story of Voyager begins to resemble the history of an interstellar rock, more than the history of a spacecraft. The machine was created deliberately, launched deliberately, and guided carefully through its early mission. But once its power is gone, and enough time has passed, its future resembles the motion of any small object traveling through the galaxy. The distinction is that this object carries metal shaped by human hands, instruments built for questions asked on Earth, and a record designed to preserve something about the civilization that sent it away. 1,000,000 years will not erase the Milky Way, and even 100 million years leaves the Sun with most of its stellar lifetime still ahead. But the scale is moving steadily toward the point where the stars themselves must become part of the changing story. Voyager can outlast civilizations easily in principle, and it may outlast entire species. Yet the Sun and other stars operate on clocks billions of years long, which is where the next transformation begins. For the first time, the distant future stops being only about where Voyager moves and starts becoming about what happens to the star it left behind. The sun that once filled the spacecraft's solar system sky will continue aging even after every direct connection with Voyager is gone, slowly consuming the fuel that has kept it stable for billions of years and moving toward changes that will eventually transform the entire system from which the probe escaped. And once Voyager 1 has spent millions of years wandering through a galaxy whose stellar neighborhoods no longer resemble the ones it knew at launch, the next great change is no longer another passing star, but the slow aging of the sun itself and the distant future of the solar system Voyager left behind. For a very long time, the sun would remain almost unchanged compared with everything happening on Earth. Because stars like ours evolve so slowly that civilizations can rise and disappear while the same familiar light continues shining. Voyager could drift for millions, then hundreds of millions of years, through the Milky Way, while the sun still looks broadly like the star it was in 1977. But that stability is temporary. On the scale of the journey we are following, deep inside the sun, hydrogen is being converted into helium, and although the process is extraordinarily slow, it steadily changes the structure of the star. As the sun ages, it gradually becomes brighter, which means the distant future of Earth begins changing long before the sun reaches its dramatic final stages. Over immense spans of time, the increasing energy reaching our planet would alter climate and oceans in ways that make the surface less friendly to the life that exists today. The exact path depends on complicated planetary processes, but the broad direction is clear. Earth does not remain permanently comfortable simply because the sun remains on the main sequence for billions of years. Voyager, meanwhile, would know nothing about this. By then, it could be separated from the sun by a vast and changing galactic distance, following an orbit shaped by the Milky Way, while the star it escaped from slowly becomes more luminous. The spacecraft would not receive a final warning from home and would not change direction when Earth begins losing the conditions that once supported oceans, forests, cities, and every person involved in the Voyager mission. Its connection with the solar system would exist only through history and through the material attached to its body. That makes the golden record increasingly strange as billions of years approach, because it preserves sounds of rain, surf, animals, human voices, and music from a planet that may no longer resemble the world represented on the disk. The record was designed as a message about Earth, but time turns it into evidence of a particular Earth, one that existed during a narrow period when liquid oceans covered much of the surface, and a technological species had only recently learned how to send machines beyond the outer planets. Eventually, after roughly 5 billion more years, the sun will begin running out of hydrogen in its central region and move away from the long, stable phase that has defined most of its life. The core will contract while the outer layers expand, and the sun will grow into a red giant far larger and brighter than the star we see today. From the perspective of the solar system, this will be one of the greatest transformations since the planets formed. Yet from Voyager's perspective, it would be another distant event occurring around a star that may no longer occupy any special place in its sky. The inner planets would face extreme conditions during this stage. Mercury and Venus are expected to be engulfed as the sun expands, while Earth's final fate is more complicated because the orbit may move outward as the sun loses mass even as the star's outer layers extend farther into space. Whether Earth is physically swallowed or survives farther out, the planet would no longer be a habitable version of the world Voyager once knew. The oceans, atmosphere, ecosystems, and human landscapes recorded in memory would already have disappeared on timescales much shorter than this. The red giant sun would be spectacular in size, but temporary, compared with the trillions of years still ahead in Voyager's story. Its outer layers would eventually be expelled into space, leaving behind the hot, dense stellar core that becomes a white dwarf. The solar system would then contain a faint stellar remnant where a bright yellow star once stood, while any surviving planets and smaller bodies continue moving through a system that has lost a significant fraction of its original mass. The white dwarf would begin extremely hot and then cool over a period far longer than the age of the universe today. It would no longer generate energy through the same sustained fusion that powers the present sun, instead radiating away stored heat while gradually becoming dimmer. The system around it would therefore move into a quieter era, one with no sunlight resembling the day experienced on Earth, and no natural warmth capable of supporting the familiar environments preserved on Voyager's record. By then, the original meaning of Voyager's escape becomes almost impossible to recognize from the solar system itself. The spacecraft once moved outward from a bright star surrounded by 8 major planets, crossed the orbits of giant worlds, and continued into interstellar space while Earth remained a blue planet behind it. Billions of years later, the place it left behind could contain a white dwarf, altered planetary orbits, shattered or surviving worlds, and almost nothing that resembles the destination written into human memory when the probe was launched. Yet Voyager's own motion would continue under the same simple principle that has carried it since its engines stopped controlling its path. It would still respond to gravity, still move through the galaxy, and still possess momentum inherited from the early days of the mission, even though the star that once dominated every calculation has become only a compact remnant. This contrast is one of the deepest parts of the spacecraft's future, because the machine can remain mechanically simple while the universe around it goes through transformations far larger than anything its designers could ever observe. The Sun becoming a white dwarf also breaks the last intuitive connection between Voyager and the idea of going home. As long as the Sun remains recognizable, it is easy to imagine Voyager as a spacecraft that has simply traveled very far from its original system. But once the star itself has changed beyond recognition, the solar system becomes another ancient environment that no longer exists in its original form. Voyager has not merely traveled through distance, it has traveled beyond the lifetime of the place that gave the mission meaning. By this point, the Milky Way around it would also have evolved substantially. Billions of years are enough for stars to complete many journeys through the galaxy, for new stars to form and others to die, and for entire stellar populations to change. Voyager's path would have been influenced by countless distant gravitational encounters, and any attempt to trace it from present-day measurements would carry enormous uncertainty, not because physics stopped working, but because the number of changing variables becomes too large for a precise prediction to remain meaningful. This is where the title question begins revealing its real difficulty. Asking where Voyager will be in 10 trillion years sounds like a request for a coordinate, but long before we reach that age, the landmarks we would normally use for the answer have transformed. Earth changes, the Sun becomes a stellar remnant, nearby stars move away, new neighbors appear, and the galaxy itself continues developing. A future position can only make sense inside a reference frame, and every familiar reference frame from Voyager's launch era is temporary. This is possible because Voyager is not escaping the Milky Way. Its current motion is fast enough to leave the solar system, but not fast enough to escape the gravitational hold of the galaxy under ordinary circumstances. The spacecraft therefore becomes part of the Milky Way's long-term population of small objects, moving on an orbit around the galactic center in the same broad sense that stars, stellar remnants, planets, asteroids, and other debris do. It escaped one star, not the galaxy containing that star. That distinction becomes increasingly important after the Sun's death, because Voyager can no longer be understood mainly as an object traveling away from a home system. Instead, it becomes one member of an enormous galactic environment where the Sun's white dwarf and Voyager itself follow different paths, through the same gravitational structure. Their relationship is no longer one of a central star and an escaping spacecraft. It is a relationship between two objects with a shared past moving independently through a changing galaxy. Over billions of years, close stellar passages become possible often enough that some may alter Voyager's orbit more noticeably than anything encountered during the early part of its journey. Most stars would still remain far away, but a rare closer encounter could change the spacecraft's direction or speed relative to the galactic center, making later predictions even more uncertain. The cumulative history of those encounters would matter far more than the exact direction Voyager happened to be pointing when it left the solar system. The galaxy itself would not remain isolated from larger changes either. The Milky Way and Andromeda are moving toward a future interaction, and on a timescale of several billion years, their large stellar systems are expected to merge into a new galactic structure. Individual stars are so widely separated that direct stellar collisions would remain unlikely, but their orbits could be rearranged as the gravitational structure of the galaxies changes. Voyager, if still intact, would be carried through that transformation as one almost massless object among hundreds of billions of stars and remnants. For the spacecraft, a galactic merger would not look like two solid objects crashing together, because galaxies are mostly empty space, and the process unfolds over enormous times. The sky around Voyager would gradually change as stellar populations overlap and the gravitational field evolves, while the probe continues moving through a region whose large-scale structure no longer resembles the Milky Way charted from Earth today. The name of the galaxy would be a historical label for a form that no longer exists in the same way. This gives Voyager's journey a strange kind of continuity. The spacecraft may survive the civilization that built it, the biosphere that produced that civilization, the familiar surface of Earth, the stable lifetime of the Sun, and even the recognizable structure of the Milky Way. Yet, it does not survive by resisting those changes. It simply happens to be small enough, cold enough, and isolated enough that many transformations pass around it without requiring the object itself to do anything. After the Sun becomes a white dwarf, there will still be trillions of years left before the time named in the title. The death of our star, which feels almost unimaginably remote from the present, occurs early in Voyager's full 10 trillion year timeline. If 10 trillion years were compressed into a single year, the Sun's red giant transformation would happen within the opening hours, leaving almost the entire imaginary year still ahead. That comparison reveals how little of Voyager's future has been covered, even after we have watched the solar system age past recognition. The spacecraft has already outlived the world that launched it in every meaningful sense. Yet, the universe still contains vast populations of stars, with lifetimes far longer than the Sun's remaining years. Small red dwarfs can continue burning for extraordinary periods, and the galaxy still has an immense future before the era of ordinary starlight begins approaching its end. Voyager would enter that future without the Sun as a familiar anchor, and without the Milky Way remaining exactly the galaxy it once left. Its story would become inseparable from the long evolution of stars, remnants, and the changing galactic structure carrying it through space. While the distance between its launch and its present condition grows so large that the word spacecraft begins to sound almost temporary. And once the Sun has faded into a white dwarf, and the solar system has become an ancient remnant of the place Voyager 1 once called home, the journey belongs almost entirely to the galaxy itself, whose stars, orbits, and structure will keep changing around the spacecraft for timescales far greater than the life of our Sun. By then, the Milky Way would no longer be the calm background that seems to surround Voyager today, because galaxies are not permanent arrangements of stars, even when their evolution appears slow from a human perspective. Their shapes are held together by gravity. Their stars move continuously through them. Gas is consumed or expelled, new stars form while older ones die, and interactions with other galaxies can rearrange enormous regions over billions of years. Voyager would be caught inside that process, as an object far too small to influence anything around it, yet still forced to follow the changing gravitational landscape wherever it leads. The most dramatic transformation expected in the relatively near galactic future is the long interaction between the Milky Way and Andromeda, two enormous galaxies moving toward one another while the space between them gradually closes. The event would not resemble two solid objects crashing together, because the distances between individual stars are so large that direct stellar collisions would remain rare, but the combined gravity of both galaxies would stretch, distort, and redistribute their stars over a period lasting billions of years. Spiral arms could lose their familiar form, stellar orbits would be altered, and what we call the Milky Way today would eventually become part of a new structure whose appearance would be very different from the galaxy shown in modern astronomy books. Voyager would not experience this as a sudden catastrophe. There would be no wall of stars rushing toward it, and no single moment when one galaxy becomes another, because the process is slow enough that even enormous changes unfold across times longer than entire planetary histories. From the spacecraft's position, the sky could gradually become richer in stars as the two systems overlap, then change again as the combined structure relaxes into a different shape. What would look dramatic in a simulation compressed into seconds would, for Voyager, be another long period of silent motion through darkness. This is also where the original direction of Voyager's escape becomes less important than the orbit it eventually follows through the galactic system. The spacecraft left the solar system with a velocity determined by its planetary flybys, but after billions of years, the larger gravitational field dominates the geometry of its journey. A close passage near a star could bend its path slightly. Another encounter much later could change it again, and the overall orbit through the galaxy would gradually become something no mission designer in 1977 could meaningfully draw on a chart. Even if nothing ever passes especially close, the galaxy itself keeps changing beneath the spacecraft. Stars are born in clouds of gas, live for different lengths of time depending on their mass, and eventually become white dwarfs, neutron stars, or black holes, while the supply of cold gas available for new stars slowly changes. The Milky Way we see today is filled with active star formation, glowing nebulae, young stellar groups, and bright massive stars that live quickly and die violently. But the deep future would gradually contain a larger fraction of older, dimmer, longer-lived objects. Voyager could therefore move through regions that become quieter, not because the spacecraft is traveling into empty space outside the galaxy, but because the galaxy itself is aging. Bright blue stars would continue disappearing on short astronomical timescales. Some, like stars, would age over billions of years, and the population would become increasingly dominated by small red stars and stellar remnants that can survive much longer. The night sky, if anyone could stand beside Voyager to see it, would not simply be darker because the spacecraft is far from Earth. It would be darker because the universe is slowly losing many of the luminous stars familiar to us now. That process would not happen uniformly, because different stars have very different lifetimes. Massive stars can live only millions of years before exhausting their fuel, while stars smaller than the Sun can remain active for vastly longer. The smallest red dwarfs burn their fuel so slowly that they can shine for trillions of years, which means they would become some of the last ordinary stars still producing light, long after the Sun has cooled as a white dwarf. Voyager's future eventually becomes a story told among these survivors. Before reaching that age, however, the galaxy would pass through an enormous period in which stellar remnants steadily accumulate. Every generation of stars leaves something behind, and over time the balance between bright stars and dark remnants shifts. White dwarfs cool gradually, neutron stars remain compact and faint, black holes persist, and planets or smaller bodies may continue orbiting objects that no longer provide anything resembling ordinary sunlight. Voyager would wander through a galaxy increasingly filled with the remains of earlier stellar generations. The spacecraft might pass near objects that did not even exist when it was launched, because stars born billions of years after 1977 could complete their entire lives before Voyager reaches the time periods we are considering. A star could form from a cloud of gas, develop planets, shine for billions of years, die, and leave behind a remnant, while Voyager continues somewhere else in the same broad galactic system. Entire stellar biographies could fit inside one quiet portion of the probe's journey. That comparison makes the scale of the future easier to feel, because Voyager does not need to move especially fast to outlast enormous changes. Its speed matters far less than the absence of a destination and the lack of any mechanism that forces its journey to end. A spacecraft carrying people would be limited by life support, fuel, maintenance, and the lifetime of its crew. But a dead machine can continue as long as nothing destroys it. Time becomes the main engine of the story. The question of destruction becomes more important as these spans grow, because a rare event that is negligible over 10,000 years can become more significant over billions. A sufficiently close stellar encounter could alter Voyager's orbit dramatically, while a direct collision with a planet, star, or compact object would end the recognizable spacecraft entirely. Although such impacts remain extraordinarily unlikely because space is so empty. More subtle damage from dust and energetic particles could slowly change surfaces and delicate structures without immediately destroying the main body. There is also the possibility that the spacecraft could eventually be ejected into a different galactic orbit through gravitational encounters, especially in a galaxy whose structure has been disturbed by mergers and long-term stellar interactions. Small objects can exchange energy during close encounters, and over enough time, some are pushed onto wider orbits while others move inward. Voyager may remain deep inside the merged galactic system, move toward its outskirts, or follow a path that present-day measurements could never identify precisely. This is one reason any image of Voyager simply circling the galactic center on a neat, unchanging orbit would be misleading. The real environment contains stars, remnants, molecular clouds, and a changing gravitational field, all interacting across enormous periods. The spacecraft is effectively a test particle in a system whose future cannot be projected with perfect detail. So, after enough time, we can describe the kind of environment Voyager probably remains in, without pretending to know the exact route it takes through every century. As gas available for forming new stars becomes less abundant, the galaxy's appearance would begin changing from the bright, structured system we know today towards something older and quieter. The glowing clouds that mark stellar nurseries would become less common, massive stars would be replenished less often, and long-lived low-mass stars would dominate the remaining ordinary light. The change would be gradual enough that there is no single year when someone could say the modern age of the galaxy has ended, yet the direction becomes unmistakable over vast time. Voyager would pass through this aging galaxy carrying images of a completely different one. The golden record contains a representation of the solar system and information intended to identify the location of the sun, but by the time trillions of years begin approaching, the star map around that origin would have been altered beyond recognition. The sun would be a darkening white dwarf. Nearby stars from the launch era would have dispersed, and the larger galactic structure would no longer match the environment from which the map was created. For Voyager itself, nothing about this matters. It would not know whether the galaxy around it still has spiral arms, whether the sun is identifiable, or whether the record remains readable. The spacecraft has no awareness of becoming ancient, and this indifference gives the journey much of its strange calmness. The universe changes, but the object simply continues following gravity. Hundreds of billions of years after launch, the galaxy would be older than any structure humans have ever observed directly by an almost impossible margin. Many stars visible today would have become remnants, while the longest-lived red dwarfs would still be burning with remarkable patience. The sky would contain fewer bright, short-lived stars, and the remaining luminous population would increasingly consist of small stars that were easy to overlook during the present era. At this scale, even galactic orbits repeat many times. Voyager could circle through the broad gravitational system again and again, while stellar neighborhoods come and go, which means the idea of one continuous outward journey from Earth has completely disappeared. There is no meaningful ahead or behind relative to the launch point anymore. There is only an old artifact moving through a system whose own history has become vastly longer than the age of the universe when Voyager was built. The galaxy would also continue losing objects through gravitational interactions. Over extremely long periods, close encounters can transfer energy in ways that gradually send some stars and smaller bodies outward, while others become more tightly bound. A slow reshuffling that changes the population over time. Voyager, with almost no mass compared with the stars around it, would simply participate in whatever encounters happened to cross its path. And one rare interaction could change its future far more than billions of years of quiet drifting. This makes the spacecraft's exact location at 1 trillion years impossible to state responsibly from the information we have today. We can say that it would most likely still be moving within or around the long-evolved descendant of the Milky Way, if it has not been destroyed or strongly ejected. But a coordinate would be fiction rather than prediction. The scientifically meaningful story is the range of futures allowed by the galaxy's evolution, not a dot placed confidently on a map that no longer exists. 1 trillion years is where the scale begins to feel genuinely alien, even by astronomical standards. It is more than 70 times the present age of the universe, long enough for the Sun to have spent almost all of that period as a cooling remnant, and long enough for the stellar population around Voyager to be dominated by stars with extraordinarily slow lives. The bright universe familiar to us would already belong to deep history. And even then, Voyager would still be only 1/10 of the way toward the 10 trillion year mark in the title, which means the aging of the Milky Way, the death of the Sun, and the disappearance of most familiar stars all happen before the spacecraft reaches the final stretch of the journey we are trying to imagine. By the time Voyager approaches its first trillion years in the darkening descendant of the Milky Way, the question is no longer whether the galaxy around it has changed, but how much ordinary starlight can remain when even the longest-lived stars have begun carrying almost the entire luminous future of the universe. 1 trillion years is difficult to compare with anything familiar, because the universe itself is only a small fraction of that age today. The Sun's entire life, from its formation to its final existence as a cooling white dwarf, would occupy only a tiny part of the interval Voyager has now crossed. The rise and fall of human civilization would be almost invisible on the same scale, while even the great transformations of the Milky Way would belong to a much earlier period. Yet the universe at 1 trillion years would not be completely dark, because some of the smallest stars are built to consume their fuel with extraordinary patience. Red dwarfs are faint compared with the Sun, but their small mass is exactly what allows them to survive for so long. Their interiors circulate material efficiently, bringing fresh hydrogen into regions where fusion can continue. And because they release energy slowly, the lowest mass examples can remain active for trillions of years. Stars that seem modest in the present universe therefore become increasingly important in the far future, not because they suddenly grow brighter, but because so many larger stars have already disappeared. For Voyager, this means the sky around 1 trillion years could still contain genuine stars, rather than only dead remnants. although the population would look very different from the one recorded at launch. The brilliant short-lived stars that dominate many modern images of the galaxy would be long gone. Sun-like stars would have spent almost all of this time as remnants, and the surviving points of ordinary stellar light would be concentrated among small red stars whose lifetimes can exceed the present age of the universe by hundreds of times. The change would have happened so slowly that there would be no single night when the galaxy suddenly became dark. Generation after generation of stars would disappear, star formation would decline, and the brightest members of the population would become less common until the remaining light was increasingly supplied by stars that had always been easy to overlook. Voyager would drift through that transition without an instrument left to measure it, while the universe around the spacecraft gradually becomes dominated by objects whose energy output is far lower than the stars humans are used to seeing. Even the idea of a galaxy would feel different by then. The descendant of the Milky Way and Andromeda could still remain gravitationally bound as a large collection of stars, stellar remnants, planets, smaller bodies, dark matter, and black holes, but the neat spiral structure, familiar from the present era, would belong to distant history. Long-term gravitational interactions would continue rearranging orbits, and some objects would slowly be pushed toward wider paths or expelled entirely, while others fall deeper into the system. Voyager would participate in that evolution without belonging to any special category as far as gravity is concerned. Its human origin would not protect it from a stellar encounter, and its small mass would make it easy for the motion of much larger objects to redirect its path. A close passage could alter its galactic orbit, while a sequence of weaker encounters could gradually move it into a region very different from the one it occupied billions of years earlier. This is why tracing a line from its current trajectory to a precise location 1 trillion years ahead would have almost no scientific meaning. The spacecraft could still be somewhere inside the gravitationally bound remnant of our local galactic system. But it could also have been scattered onto a very wide orbit, or even ejected into the space beyond it if the right sequence of encounters occurred. None of these outcomes can be selected confidently from present-day information. Over such an enormous interval, the uncertainty is not a small blur around a known destination. It becomes part of the story itself. If Voyager were thrown outward into intergalactic space, its surroundings would become even emptier than the regions it crosses today. The universe would continue expanding on large scales, carrying distant galaxy groups farther apart, while a small artifact between them could spend extraordinary periods with no nearby star at all. If it remained within the old galactic system instead, it could still pass through regions populated by red dwarfs and dark stellar remnants. But even there, the typical distances between objects would leave most of its journey almost completely uneventful. At 1 trillion years, that constructed origin would be astonishingly ancient. Any natural object nearby could also be extremely old, but Voyager would carry signs of deliberate organization created during a moment when the universe was still filled with bright galaxies and abundant starlight. It would be a technological fossil from an era so early that the universe around it might no longer offer many visible clues to what the sky looked like when the spacecraft was launched. The golden record would be even more unusual in that context, because its content describes not merely a civilization, but an entire sensory environment that may have vanished from the region of space where the message began. Rain, ocean waves, animal calls, music, machinery, and human speech all belong to a wet, living planet orbiting an active yellow star. At 1 trillion years, the Sun would have been a stellar remnant for almost the entire age represented here, and Earth itself may no longer exist in any recognizable form. There is no reason to assume such an observer will ever appear, and Voyager's most probable experience remains no experience at all. The spacecraft has no awareness of the universe growing old around it, no memory of the planets it once visited, and no way to distinguish 1 trillion years from a single, quiet second. The meaning comes entirely from our decision to follow the object forward and compare its persistence with everything else that changes. That comparison also reveals how misleading the phrase "old spacecraft" becomes. A trillion-year-old Voyager would not simply be an unusually ancient machine. It would belong to a different cosmic age from the one in which machines were first built. The stars used for navigation during its launch would have completed their lives or moved far from their original positions. The Milky Way would have changed form, and the universe, visible from its location, could contain far fewer bright landmarks than the sky humans knew. The longest-lived red dwarfs would provide one of the few forms of continuity. A low-mass star that formed near the era of Voyager's launch could still be shining after 1 trillion years, having used only part of the enormous lifetime available to it. This means Voyager might pass through a galaxy where nearly everything familiar is gone, while some humble stars that already existed in 1977 continue burning, linking the early universe of humanity with a future almost too distant to describe. Those stars would not remain unchanged forever. Their extremely slow consumption of hydrogen only delays the end, rather than preventing it. And as trillions of years accumulate, they too begin moving toward the final stages of their evolution. The exact behavior depends on their mass. But the important point is that ordinary stellar fusion still has a limit. Even the most economical stars eventually use the fuel that made them luminous. That gives the trillion-year universe a different kind of tension from the billions of years that came before. Earlier, the death of one star could be balanced by the existence of countless others, while now, the population capable of producing ordinary starlight is narrowing toward the smallest survivors. The universe is not dark yet, but it is moving toward a time when the disappearance of those stars removes one of the last great sources of natural visible light. Voyager might spend vast periods with no bright star near enough to cast more than a faint glow across its surface. The sun once illuminated the spacecraft strongly enough that the outer planets could be photographed using reflected light. But at 1 trillion years, the probe may cross environments where the nearest active star is only another dim point at an enormous distance. The metals of Voyager would not gleam against a dramatic background. Most of the time, they would sit almost completely dark. Voyager fits naturally into this dark inventory. It began as one of the brightest examples of human engineering, only because people on Earth knew where to point antennas and understood what its faint signals meant. But without communication, it becomes another cold object among countless others. Its value is historical rather than energetic. The galaxy does not notice the difference between a spacecraft and a small piece of natural debris. Gravity does, however, continue treating every object according to mass and motion, so the long reshuffling of the galactic system never truly stops. Encounters between stars and remnants can exchange energy, and over vast periods, some bodies are pushed outward while others settle into more tightly bound regions. Voyager could experience many such distant influences, which makes its trillion-year location less like a destination and more like the result of an enormous sequence of interactions that cannot be reconstructed from the present. The surviving red dwarfs would continue burning through much of that span, but their dominance makes the direction of the universe increasingly clear. As the clock advances from 1 trillion towards several trillion years, more of the remaining ordinary stars move through their long lives, while stellar remnants continue accumulating and fresh star formation becomes less significant. The bright age of the universe narrows slowly rather than ending in a single event. Voyager could cross this entire transition without ever passing close enough to one of those final stars for the encounter to feel dramatic. A star may brighten slightly in the distance over thousands or millions of years, reach a closest approach while remaining separated by an enormous gulf, and then fade behind again. To a machine with no functioning camera, even the last stars in the universe would be silent events. That is perhaps the strangest scale Voyager introduces into the story. The disappearance of ordinary stars sounds like an ending when described from Earth. But for the spacecraft, it is simply another change in the background, through which momentum carries it. There is no boundary for Voyager to cross when the universe becomes old, just fewer sources of light around an object already accustomed to darkness. By several trillion years, the exact identity of the galactic system containing Voyager may matter less than the fact that it belongs to a universe dominated increasingly by long-lived small stars and dead remnants. The spacecraft could remain gravitationally associated with the descendants of our local galaxies, or could have been scattered far away, yet either route leads into the same broader cosmic trend. Ordinary starlight becomes rarer as the final efficient stars approach the end of their astonishing lives. The 10 trillion year mark therefore begins to look less like an arbitrary large number and more like a meaningful boundary in stellar history. The smallest red dwarfs can have lifetimes measured in trillions of years. So the age in the title carries Voyager toward an era when some of the longest-lived ordinary stars are finally reaching limits that larger stars reached billions of years earlier. Voyager started its journey beneath a sky filled with stars, at every stage of life, from young stellar nurseries to ancient red giants. But the farther we move into the trillion-year future, the more that diversity collapses into remnants and a shrinking population of small survivors. The spacecraft is no closer to a destination, yet the universe around it is moving toward one of its greatest transitions. And as Voyager 1 leaves its first trillion years behind and continues toward 10 trillion, the remaining red dwarfs become more than faint background stars, because their final light marks the last long stretch of the stellar universe before even the most patient stars begin to fade. For most of cosmic history as we understand it today, stars are the obvious landmarks of the universe. They gather into galaxies, illuminate clouds of gas, warm planets, and provide the visible structure that makes space seem populated rather than empty. Voyager began its journey during this bright era, when the Milky Way contained hundreds of billions of stars and the night sky from Earth appeared crowded with points of light. Several trillion years later, that familiar condition would no longer be something the universe could take for granted, because the stars capable of surviving for such enormous periods are the smallest and faintest members of the population. A red dwarf survives by spending its fuel slowly, and the lower its mass, the more extreme that patience can become. While the Sun uses its central hydrogen over roughly 10 billion years, the smallest hydrogen-burning stars can remain active for trillions of years, with some estimates extending their lives to around 10 trillion years or beyond. Their faintness, which makes them easy to overlook in the present-day sky, becomes their great advantage in the future. They do not need to burn brightly to remain stars. They need only continue converting hydrogen into helium, slowly enough that gravity and pressure remain balanced for an almost unimaginable length of time. Voyager could therefore spend trillions of years in a universe where the dominant living stars are not brilliant suns, but dim red points, scattered among far larger numbers of dead remnants. White dwarfs would have cooled for ages. Neutron stars would remain compact and difficult to see. And black holes would persist as gravitational objects, without producing much light, unless matter happened to fall toward them. Planets and smaller bodies could survive around some of these remnants, or wander freely after their systems were disturbed, leaving enormous amounts of matter in space, even as visible starlight becomes increasingly rare. The change would be slow enough that no observer could identify a single moment when the stellar universe became old. A red dwarf that has already burned for 1 trillion years might continue for trillions more, while another of slightly greater mass reaches the end of its life sooner. The population would thin gradually, one star at a time, so that the universe loses light not in one final blackout, but through an extended fading that lasts longer than almost every earlier era combined. Voyager's surroundings would depend greatly on where its gravitational history has carried it by then. If the spacecraft remained inside the long-evolved descendant of the local group, it could still move through a loose population of stars and remnants held together by gravity, although that system would be far older and darker than any galaxy visible today. If earlier encounters had pushed Voyager outward, it might instead be traveling through the space beyond the main stellar population, where the nearest surviving star could be separated from it by an extraordinary distance. Every stellar encounter along that path would add uncertainty to the question of location. Most flybys would remain distant, but trillions of years provide an enormous number of opportunities for the spacecraft to pass through changing neighborhoods, and one unusually close encounter could redirect it significantly. It might be accelerated onto a wider orbit through the galactic remnant, scattered toward a more central region, or pushed outward into a path from which it never returns. We cannot choose among those possibilities from present-day measurements because the exact sequence of encounters is unknowable across such a span. This does not make the story meaningless. It simply changes the kind of question we can answer. We cannot draw a reliable map showing Voyager's exact route through 10 trillion years, but we can describe the universe through which some surviving version of the spacecraft would have to move. That universe becomes older, dimmer, more dominated by remnants, and increasingly dependent on low-mass stars for the ordinary starlight that remains. The red dwarfs themselves would also change in ways that differ from the familiar evolution of the Sun, because the smallest examples can mix much of their material throughout their interiors. They use hydrogen more completely than a Sun-like star does. They do not simply repeat the Sun's path on a slower schedule, and their final evolution can occur without the same dramatic red giant stage expected for our star. Over trillions of years, they gradually alter their composition and structure until even their exceptional fuel economy reaches a limit. That matters because the universe near 10 trillion years is not simply the present universe with fewer stars. The types of stars still active would have been selected by time itself. Anything that burns fuel rapidly is gone, while only objects designed by physics to release energy slowly remain. The sky becomes a record of survival, where brightness is almost the opposite of longevity, and the stars that once looked least impressive outlast the giants by trillions of years. A close passage by one of the remaining stars could warm part of the spacecraft slightly or expose it to a denser environment, while a distant passage would change almost nothing except the probe's trajectory. If planets still orbited some of these stars, Voyager would almost certainly miss them by enormous distances, because a planetary system occupies only a tiny volume compared with the space between stars. Even in the final ages of starlight, the most likely experience remains a long crossing through emptiness. The golden record would still provide the strongest connection to the universe Voyager came from, assuming enough of it survived to remain recognizable. Its diagrams describe the solar system and the location of the Sun, using references chosen when the local galaxy had a completely different stellar arrangement. Its images show a bright world with oceans, clouds, landscapes, living organisms, and human beings, while its sounds preserve a planet full of weather and biological activity. By several trillion years, every one of those references would belong to an era almost unimaginably remote. Yet the message itself is fixed. The greetings do not update, the music does not change, and the map does not follow the motion of the stars. Voyager carries one frozen moment while everything outside it keeps moving, which means the artifact becomes increasingly detached from the era it describes. If the record remained readable, its greatest information might eventually be not what humanity intended to say, but simply the fact that such a bright and biologically rich environment once existed at all. As the clock moves through 2 trillion years, 3 trillion and farther, the longest-lived stars continue doing something the Sun could never do, remaining ordinary stars while almost every familiar stellar generation belongs to the distant past. The concept of a current star population would become dominated by objects that were already ancient, compared with today's universe, yet even their extraordinary lifetimes remain finite. By then, the chance that the spacecraft has remained perfectly intact would be impossible to defend. Trillions of years leave room for damage from microscopic impacts, radiation, material degradation, and rare encounters that no model can predict individually. The useful question is not whether Voyager still looks exactly like the photographs taken before launch, but whether some coherent remnant of the spacecraft could remain, carrying enough structure or material to connect it with the original object. A collision does not have to vaporize the entire spacecraft to change that answer. A sufficiently energetic impact might tear away an antenna or instrument boom, while repeated smaller events could gradually roughen surfaces and weaken components. Over enough time, Voyager could become a collection of damaged pieces, traveling along related paths, rather than one clean spacecraft. And at some point, the phrase, "Where is Voyager 1?" would itself become ambiguous if the artifact no longer exists as a single connected object. That possibility is important because 10 trillion years is so long that survival can no longer be treated as a background assumption. A trajectory tells us where an object would go if the object continues existing, while physical survival asks whether there is still an object to follow. These are different questions, and the closer we move toward the final age in the title, the more they begin to overlap. Even without a catastrophic collision, the golden record is not guaranteed to remain readable. The electronics are not expected to function, and many materials may change on timescales vastly shorter than the full journey. Voyager's strongest claim to persistence comes from being far from atmospheres, liquid water, active geology, and other environments that destroy objects quickly, but deep space offers protection only in a relative sense. It slows many forms of change. It does not eliminate time. The stars around it face the same basic truth on a much larger scale. Red dwarfs live far longer than the sun because they spend fuel slowly, yet they do not possess an infinite supply. As the universe approaches the upper end of their possible lifetimes, more of these stars finally leave the long, stable phase that allowed them to dominate the late stellar era. Their disappearance makes the background around Voyager darker in a physical sense, not merely more distant from Earth. Voyager would have begun in one of the richest eras for visible cosmic structure, and survived, if it survives at all, into a universe where ordinary light is becoming exceptional. That contrast is more important than any exact distance traveled. The spacecraft may have covered enormous paths through the galactic remnant, perhaps circling its gravitational system many times. Yet the greater journey is through changing cosmic conditions, rather than simple kilometers. 7 trillion years, 8 trillion, and 9 trillion carry the remaining low-mass stars closer to the ends of their lives, while the exact condition of Voyager becomes less certain with every additional span. Its route could lie among old stellar remnants, far outside the main galactic population, or somewhere no present-day map can define. But wherever the probe has gone, it would belong to a universe much closer to the end of ordinary stellar burning than to its beginning. At this stage, the title's number stops functioning merely as a dramatic distance into the future and becomes a real astrophysical threshold. Low-mass red dwarfs can survive for trillions of years, with some estimates reaching roughly 14 trillion years. So 10 trillion years does not place Voyager after every star has vanished. Instead, it carries the spacecraft into the period when the oldest and smallest ordinary stars are among the few remaining natural sources of long-lasting starlight. That distinction matters because the universe at 10 trillion years is not completely black. Some red dwarfs may still be active, especially depending on their exact mass and age, while others will already have exhausted the long hydrogen-burning phases that made them survivors. Voyager would therefore arrive not at a clean ending, but in the middle of a prolonged transition, surrounded by a mixture of faint living stars and the remnants of countless stellar generations. And through all of this, Voyager would carry no awareness that it has reached the age written in our question. 10 trillion years is meaningful to us, because we chose the number before beginning the journey. But nature provides no clock striking midnight when the moment arrives. The spacecraft simply continues from one second into the next, while the last, long-lived stars continue changing around it. The more important question is what exactly remains of Voyager by then, and what kind of cosmic environment surrounds whatever survives. Because only after answering those two uncertainties can we return to the title and ask where a human-made object could honestly be said to exist after 10 trillion years. And as the final trillion years before that moment pass around Voyager 1, the fading red dwarfs bring the spacecraft to the edge of the age named in the title, where the problem is no longer merely following its path through space, but deciding what may still be left to follow at all. 10 trillion years after launch, the universe would still contain matter, gravity, stellar remnants, and at least some ordinary stars. But almost every familiar feature of the sky would belong to an era so distant that the word ancient barely begins to describe it. The sun would have spent almost the entire interval as a cooling white dwarf. The structure once called the Milky Way would have been transformed by galactic evolution, and the stars that surrounded Earth in 1977 would have completed their lives or moved through countless different neighborhoods. Voyager, if any recognizable part of it remained, would exist inside a cosmos that had aged hundreds of times beyond the universe we know today. The number itself can create the misleading impression that all stars must already be gone, but the smallest red dwarfs are capable of burning hydrogen for astonishingly long periods. Some low-mass stars may remain active for roughly 10 trillion years or even longer, which means Voyager would not necessarily arrive in a universe of absolute darkness. Instead, it would reach a late stage of the stellar era, when ordinary starlight has become scarce, concentrated among the most efficient stars ever formed, while the remains of earlier stellar generations dominate much of the mass around them. A surviving red dwarf at this age would be almost the opposite of the stars that attracted human attention during Voyager's original mission. It would not be large, bright, or spectacular, yet its faintness would have allowed it to endure while stars like the Sun vanished trillions of years earlier. The sky around Voyager could therefore contain a small number of dim stellar lights, separated by enormous regions, populated mostly by dark objects. Depending on whether the spacecraft remained inside a bound galactic remnant or had been scattered into a more isolated orbit long before. There is no reliable way to know which of those environments Voyager would occupy, because the spacecraft would have passed through an unimaginable sequence of gravitational interactions after leaving the solar system. The broad gravitational field of the galaxy would shape its motion. Passing stars would alter its trajectory by different amounts. Mergers and long-term stellar encounters would rearrange the system itself, and small uncertainties in every early prediction would have had trillions of years to grow. A precise coordinate at this age would therefore suggest a level of certainty that science cannot honestly provide. The meaningful answer has to be wider. Voyager could still be orbiting somewhere within the old gravitational descendant of the local group, perhaps moving through a sparse region filled with red dwarfs, white dwarfs, neutron stars, black holes, planets, and smaller debris. It could instead occupy a very wide orbit far from the denser stellar population. Or it might have been ejected through gravitational encounters and now travel through intergalactic space. These possibilities are not different versions of the same map. They are fundamentally different environments produced by a history too long to reconstruct exactly. If Voyager remained gravitationally bound to the evolved galactic system, it might have completed many orbits around its center during the 10 trillion years since launch. The idea of the spacecraft steadily flying farther from Earth would have stopped making sense long before, because neither Earth, the Sun, nor Voyager would occupy fixed positions inside the galaxy. The spacecraft could move inward during one portion of its orbit and outward during another, while encounters with other objects gradually reshape that motion. If it had been ejected instead, the journey would become quieter still. Outside a bound galaxy, Voyager might move through regions where the nearest star lies at a distance that makes even the emptiness of present-day interstellar space seem crowded by comparison. The expanding universe would continue increasing the separation between distant, unbound structures, and a small artificial object could spend ages crossing darkness with no nearby source of visible light strong enough to illuminate its surface in any meaningful way. This would not stop Voyager from moving. The spacecraft does not require surrounding stars in order to preserve its momentum, and empty space offers no ordinary friction capable of bringing it gradually to rest. Its velocity could change through gravity, but the absence of an engine does not imply the absence of motion. 10 trillion years after launch, whatever remains of Voyager could still be following a trajectory created ultimately by the planetary encounters that accelerated it away from the Sun, even though that original path has been modified beyond recognition. The environment around it would be dominated increasingly by objects that do not shine like normal stars. White dwarfs from ancient stellar generations would have cooled enormously. Neutron stars would be faint, unless some unusual process made them visible, and black holes could remain almost invisible when no surrounding matter is falling toward them. Cold planets and smaller bodies might continue drifting through space or orbiting dead remnants, leaving a universe that contains far more structure than the darkness alone would reveal. Against that future, the golden record becomes almost impossible to place emotionally. The images stored on it describe oceans under sunlight, clouds moving across a blue atmosphere, animals, plants, human bodies, cities, mathematics, and the architecture of a planetary system around a bright main sequence star. The sounds carry weather, biological life, spoken greetings, machinery, and music. At 10 trillion years, those recordings would describe conditions belonging to an early stellar universe, whose ordinary brightness had largely disappeared. Even if the record survived physically, anyone discovering it would face a message detached from nearly every astronomical reference visible around the spacecraft. The Sun would no longer resemble the star described by the record. Nearby pulsars and stellar positions would have changed or vanished, and the galactic environment would have undergone transformations lasting trillions of years. Reconstructing the message's origin could require understanding not merely another place, but an entirely different age of the cosmos. Yet reaching this point does not provide the clean ending the title might seem to promise. 10 trillion years is not a wall in time, and there is no universal event scheduled to occur at that exact age. Some red dwarfs may still be shining, while others have reached late stages of evolution. Stellar remnants would continue existing, gravity would continue acting, and Voyager's trajectory would continue if the artifact itself survived. The number is useful because it places the spacecraft near a profound transition in stellar history, not because the universe suddenly switches off. The longest-lived, low-mass stars are particularly important here because their lifetimes depend strongly on mass and internal behavior. A star, somewhat heavier than the smallest red dwarfs, would finish its main sequence life much earlier, while one near the lowest mass capable of sustaining hydrogen fusion could continue for trillions of years longer than the Sun. This spreads the end of ordinary stellar burning across a broad interval, rather than concentrating it at one date. Voyager could therefore pass 10 trillion years, while faint stars remain scattered somewhere in its cosmic neighborhood. And there may be no way to tell whether the nearest one is a few light-years away or vastly farther without knowing the spacecraft's actual gravitational history. The title asks for a location, but by this stage, even describing the surrounding light requires uncertainty, because location determines which remnants and surviving stars happen to share the same region. That uncertainty is not a weakness in the story. It is the scientifically honest result of extending one small object's future across a timescale far beyond anything directly observable. We know enough physics to describe how low-mass stars age, how gravitational systems evolve broadly, and why the universe becomes dimmer. But we do not possess information precise enough to replay every gravitational encounter Voyager could experience for 10 trillion years. The farther we move beyond the measured era, the more responsible the answer must shift from exact prediction toward possible physical histories. One of those histories leaves Voyager inside a sparse but still bound stellar system, moving among red dwarfs and dark remnants. Another sends it far into the outskirts after repeated gravitational encounters, where active stars become rare points at extreme distances. A more dramatic but less predictable event could capture it temporarily around a star or compact remnant, while an unlucky collision could end the spacecraft's recognizable existence long before any of these futures arrive. The title cannot tell us which branch nature chooses. What remains consistent across nearly all surviving possibilities is the loss of the solar system as a useful home reference. Earth may not remain recognizable. The Sun is no longer an ordinary star, and the exact place where Voyager began has spent trillions of years moving through a transformed galactic environment. Saying that the spacecraft is a certain number of light-years from Earth would offer little intuitive meaning, even if such a distance could somehow be calculated, because the Earth attached to the original journey belongs to an unimaginably ancient past. But the object itself cannot be treated as unchanged, while everything else ages. Voyager was constructed from materials chosen to survive launch, radiation, vacuum, and decades of operation, not trillions of years. Its electronics, insulation, coatings, joints, exposed surfaces, record cover, antenna, booms, and structural components all face environments that act slowly but never stop acting entirely. The enormous emptiness of space protects the probe from many destructive processes found on planets. Yet protection is not the same as immortality. Radiation would continue passing through the spacecraft, energetic particles would alter materials at microscopic scales, and dust impacts would occur rarely, but at potentially high relative velocities. Most individual events may do little, while one unfortunate collision could damage a large part of the probe. Across a few decades, these risks are manageable. Across 10 trillion years, the cumulative question becomes fundamentally different. Even the phrase Voyager 1 becomes something we need to define. If the high-gain antenna is gone, but the central body remains, is that still Voyager? If the spacecraft breaks into several pieces traveling along slightly different paths, which fragment receives the name? If only the golden record and part of its protective cover survive while most of the structure is destroyed, has Voyager survived, or has only one artifact from Voyager survived? These questions sound philosophical, but they matter physically because a 10 trillion year trajectory is useful only if we know what object we are following. In the early centuries of the journey, there is no ambiguity. Voyager is one spacecraft. After trillions of years of possible impacts and material changes, survival may become a spectrum rather than a simple yes or no. So at the exact age named in the title, the most honest image is not a pristine Voyager floating untouched beneath the final stars. It is a range of possibilities. Perhaps a heavily weathered spacecraft still recognizable in the darkness. Perhaps several fragments carrying portions of its original structure. Perhaps a golden record separated from the probe. Or perhaps no identifiable artifact at all, because some event long before destroyed what humanity launched. And once the universe has aged to 10 trillion years and every reliable map of Voyager's route has dissolved into uncertainty, the question that has to be answered before we can place the spacecraft anywhere is simpler and more difficult than a coordinate. Could Voyager 1 physically survive long enough for there still to be a Voyager 1 at all? The spacecraft was never built with such a timescale in mind. Its materials were selected to survive launch, years of radiation, the cold of the outer solar system, and a mission expected to last for decades rather than trillions of years. The fact that Voyager has already operated for so long is remarkable, but there is an enormous difference between remaining functional for a human lifetime and remaining physically recognizable across a period hundreds of times longer than the present age of the eyes. Universe. Once the electronics have failed and the last trace of power is gone, the question stops being whether the spacecraft works and becomes whether its structure can simply continue existing. Deep space gives Voyager 1 enormous advantage. Almost nothing is there. On Earth, exposed machinery is attacked continuously by moisture, oxygen, temperature changes, biological activity, erosion, and weather, while a spacecraft drifting between the stars avoids nearly all of those processes. There is no rain falling across the antenna, no ocean air corroding metal, and no atmosphere carrying abrasive particles against its surfaces. In that sense, interstellar space is one of the gentlest places a dead machine could remain. But gentle does not mean perfectly safe. When the clock is allowed to run for trillions of years, space contains gas, dust, cosmic rays, energetic particles, and occasional larger objects, and Voyager continues moving through all of them at high speed. A dust grain that would seem insignificant while resting on a table can carry substantial energy when two objects meet at many kilometers per second. And the spacecraft has no shield designed to remain flawless through an effectively unlimited number of such encounters. Most particles would be extremely small, and most impacts would affect only tiny areas of material, but cumulative damage becomes difficult to dismiss. Across 10 trillion years, surfaces could become scarred, coatings could be altered, thin structures could weaken, and exposed components might slowly lose the clean manufactured shapes they had when the spacecraft left Earth. Voyager does not need to be hit by a large object for time to leave a physical record on it. Billions of small interactions could gradually turn the original surface into something far rougher and more damaged. Radiation would work differently, but just as persistently. High-energy particles passing through the spacecraft can disturb atoms, damage electronic components, and alter materials at microscopic scales. During the active mission, engineers worry about radiation because it can change the behavior of instruments and electronics. But after those systems have been dead for ages, the concern becomes structural rather than operational. The spacecraft no longer needs a computer to calculate correctly, yet the materials themselves are still being exposed. The larger metallic structures may be more durable, but even they are not guaranteed immortality. The high-gain antenna, support booms, instrument housings, and central spacecraft body are all physical objects with joints, fasteners, and areas of different thickness, so damage does not have to destroy everything at once. A collision could remove one section while leaving the rest intact, or gradual weakening could allow a long boom to separate after an impact that would have been harmless when the spacecraft was new. This raises an important distinction between Voyager surviving and Voyager remaining complete. A spacecraft missing an antenna or several instruments could still clearly be identified as Voyager 1, especially if the main body and distinctive structures remained together. Even severe damage would not automatically erase its identity, because archaeologists on Earth routinely identify objects from fragments rather than from perfect preservation. The same principle could apply in deep space, where a badly damaged artifact may still preserve unmistakable signs of artificial construction. The golden record adds another layer, because it carries information in a more concentrated form than the rest of the spacecraft. If the record and its protective cover remained attached and sufficiently intact, some of the original message might survive long after the electronics had vanished as useful technology. Yet saying that the record could survive is not the same as saying it would remain perfectly playable, because surface damage, microscopic alteration, impacts, and long-term exposure could gradually affect the information stored on it. A future discoverer might therefore find something that is clearly a manufactured disk, while being unable to recover every sound and image engraved into it. Perhaps only sections remain readable. Perhaps the protective cover survives better than the record itself, or perhaps an impact removes the entire assembly from the spacecraft, while leaving both pieces on slightly different trajectories. The message from Earth could survive in fragments even if the object carrying it no longer exists in the exact arrangement imagined by its builders. This is where 10 trillion years begins changing the meaning of survival. During the first centuries, asking whether Voyager still exists is straightforward, because the spacecraft is one connected object. Across trillions of years, however, every possible collision, fracture, and separation has so much time to occur that the boundary between one spacecraft and several remnants becomes increasingly uncertain. A much larger impact could make the problem more extreme. Voyager is small enough that a collision with even a modest natural object at high relative speed could produce severe damage. And although the probability of such an event over short periods is low, 10 trillion years provides a staggering amount of opportunity. A single unlucky encounter could destroy the spacecraft long before the universe reaches the age in the title, which means any story of Voyager surviving that long has to remain conditional from beginning to end. The same is true for gravitational encounters, although they threaten the path more often than the structure itself. A close passage by a star, brown dwarf, planet, or compact remnant could redirect Voyager dramatically, while a very close encounter could expose it to stronger radiation or denser material than it would experience in ordinary interstellar space. The chance of any particular event may be tiny, but over trillions of years, the spacecraft crosses so much gravitational history that rare possibilities become harder to ignore. There is no practical way to calculate every one of these hazards for the full journey, because doing so would require knowing the exact future positions of enormous numbers of objects and the detailed evolution of the spacecraft itself. We can reason about the kinds of processes that matter, but we cannot assign Voyager a reliable personal history through every close encounter, every dust impact, and every changing stellar environment. This is why any claim that the spacecraft definitely survives intact would go far beyond what the physics can support. The opposite claim would also be too strong. There is no known rule saying that Voyager must be destroyed within a particular number of years, simply because it is old. If it spends most of its future in extremely sparse space and avoids large impacts, substantial parts of the structure could persist for extraordinary periods. Deep space does not contain a universal corrosion clock that reaches zero at a fixed date. Survival depends on the specific environment and sequence of events the object happens to encounter. That leaves us with a range rather than a single prediction. At one extreme, an unlucky collision destroys Voyager relatively early in its silent journey, perhaps long before the sun dies. At the other, the spacecraft remains largely recognizable through billions and trillions of years, gradually accumulating damage without suffering any event large enough to tear it apart. Between those extremes are countless possibilities in which some structures remain, others separate, and the artifact becomes progressively less complete, while still preserving traces of its origin. The most scientifically careful image at 10 trillion years is therefore not a flawless spacecraft, suspended exactly as it appears in museum models. If Voyager survives, it would more plausibly be an ancient altered object, perhaps missing delicate parts, carrying surfaces changed by radiation and impacts. and bearing only some of the clean geometry it had at launch. The shape might still be recognizable, but age would be written into every exposed material. Even then, the most interesting surviving feature may not be the technology itself, but the evidence of intention. Nature can produce metal-rich objects and unusual shapes, but a surviving fragment of Voyager could contain combinations and patterns that strongly suggest manufacture rather than geology. Holes arranged for fasteners, pieces of circuitry, engraved information, or the structured geometry of the record could reveal that the object was made, even if nobody could immediately determine who made it. For a future observer, that could be enough to transform Voyager from debris into archaeology. The machine would no longer be judged by whether its transmitter works or whether its instruments can take measurements. It would be judged by whether its remaining structure still carries evidence of a technological origin. A fragment no larger than part of the golden record might preserve more historical meaning than the entire dead spacecraft body, if the information on it remained partially recoverable. There is something unsettling about that possibility, because the artifact could preserve a clearer memory of Earth than the universe around it does. The sun would be a cooling remnant. Earth might be gone or unrecognizable. The nearby stars from the 20th century would have vanished or moved far away. Yet a damaged object drifting through darkness could still carry images of trees, people, animals, oceans, and the sound of rain. The record would describe a world whose natural evidence had been erased long before. At the same time, complete destruction is not required by the passage of time alone. Metals do not simply disappear because 1 trillion years has passed, and empty space removes many of the mechanisms that would quickly erase an artifact on Earth. If Voyager avoids major collisions, some of its mass may remain organized for extraordinary durations, even while fine details are lost. The surviving object could become simpler without becoming natural. That distinction is enough for the final question of the journey, because we do not need Voyager to remain operational, complete, or beautiful in order to ask where its remnants might be. We only need some identifiable part of the spacecraft to survive long enough for the word Voyager to retain physical meaning. Once that condition is accepted, the focus can shift away from materials and return to the enormous gravitational history that determines where those remnants would actually be. By 10 trillion years, no present-day calculation can follow that history precisely. Voyager may have spent ages orbiting within the descendant of the local group, may have been scattered onto a wide path through its outskirts, or may have escaped into an emptier region between bound systems. A surviving fragment could even occupy a trajectory very different from the original spacecraft if an impact or gravitational encounter separated it from the rest. The answer to where Voyager will be, therefore, depends on two uncertainties layered together: whether something identifiable survives, and which path that surviving material follows through a universe that changes continuously for 10 trillion years. Neither can be reduced honestly to one exact point on a map, but together they still allow a meaningful final picture. And if some recognizable part of Voyager 1 does survive all the way to 10 trillion years, then the last question is no longer whether it can endure, but what the laws of gravity and the long evolution of the galaxy allow us to say about where that ancient human artifact could actually be. The most important answer is also the least dramatic. Nobody can give Voyager 1 an honest coordinate 10 trillion years into the future. We know its motion extremely well on human timescales, and astronomers can integrate the paths of the spacecraft and nearby stars far enough ahead to identify future stellar encounters. But that kind of prediction becomes less precise as the interval grows. Over trillions of years, stars move through changing gravitational environments. Galaxies evolve, close passages alter orbits, and tiny uncertainties have more than enough time to become enormous differences in position. This does not mean Voyager suddenly becomes mysterious after a particular date. Its motion never stops following physics, and nothing about the spacecraft is exempt from gravity. The problem is that predicting one small object for 10 trillion years would require knowing the future gravitational history around it with a precision that no present observation can provide. A star passing slightly closer than expected millions of years from now could change Voyager's direction by a small amount, and that new direction would alter every later encounter, allowing one modest difference to grow into a completely different path after enough time. The most detailed studies of Voyager's future stellar flybys therefore focus on comparatively short astronomical intervals, extending trajectories through the galactic gravitational field over roughly the coming million years rather than pretending that the same precision can survive for trillions. Within that nearer future, Voyager 1 is expected to pass through the distant neighborhoods of other stars without actually entering them in the sense of a planetary mission. But after enough encounters, the clean extension of its present trajectory becomes less useful than the broader question of what gravitational system still contains it. If Voyager remains bound to the descendant of our local galactic system, then 10 trillion years from now, it may still be orbiting within the vast collection of old stars, stellar remnants, planets, and dark matter that grew out of the Milky Way, Andromeda, and their surrounding companions. The familiar spiral arms would be gone as recognizable landmarks. The Sun would be a cold stellar remnant, and the distribution of stars would have been rearranged repeatedly. Yet gravity could still keep Voyager within the same broad island of matter that once contained Earth. In that future, describing Voyager as being a certain distance away from Earth would hide more than it explains. Earth may no longer exist in a recognizable form. The Sun would not resemble the star that launched the spacecraft, and both the solar system's remains and Voyager would have followed independent galactic paths for trillions of years. The spacecraft might be farther from the Sun's remnant during one part of its orbit and closer during another, while neither object occupies anything resembling its present location in the galaxy. A second possibility is that repeated gravitational encounters push Voyager toward the outskirts of the old galactic system. Small objects can gain or lose orbital energy during close passages, and trillions of years provide an enormous amount of time for such changes to accumulate. Voyager could end up moving on an orbit so wide that it spends most of its time far from the denser concentration of stellar remnants, returning only slowly through a region where the remaining stars appear sparse and faint. An even more extreme path could carry the spacecraft completely out of the bound system. If the right gravitational encounter gives Voyager enough energy, a surviving fragment could be ejected into intergalactic space and continue traveling through an environment emptier than the one it knows today. Once outside the local gravitational island, it might spend extraordinary periods with no nearby star at all, while cosmic expansion continues increasing the separation between distant, unbound structures. None of these futures can be chosen confidently, and that uncertainty is the real answer hidden inside the title. Voyager will not simply travel in the same straight direction for 10 trillion years and arrive at a point that can be found by multiplying its current speed by time. That calculation would ignore the galaxy's gravity, the motion of stars, future stellar encounters, the evolution of the galactic system, and the possibility that the spacecraft's trajectory changes many times before the Sun itself has finished its life. Even its current speed does not describe a universal motion through space, because velocity is always measured relative to something. Today, we often describe Voyager's speed relative to the Sun, which makes perfect sense while discussing its escape from the solar system. 10 trillion years later, the Sun is no longer a useful central reference, and Voyager's motion would be better understood relative to whatever gravitational structure still surrounds it. This is why the image of Voyager forever racing outward into a featureless black universe is only partly correct. It is leaving the Sun, but it is not currently leaving the Milky Way, and on the longest timescales its journey belongs to galactic dynamics, rather than to a simple escape line from Earth. If nothing later ejects it, the spacecraft may spend ages orbiting inside the descendant of our galactic neighborhood, moving through different regions again and again, rather than traveling monotonically farther from the place where the solar system once existed. The word where, therefore, has to become broader than a coordinate. The scientifically meaningful answer is that a surviving Voyager could be somewhere inside the evolved gravitational remnant of our local galaxies, somewhere on its distant outskirts, or somewhere beyond it after a later ejection, while any exact position among those possibilities is unknowable from the information available today. 10 trillion years creates too much gravitational history between the spacecraft we can measure now and the artifact we are trying to place in the far future. What can be predicted more confidently is the kind of universe surrounding it. The brilliant stellar population of the present day would be largely gone. The Sun would have become a remnant trillions of years earlier, and the remaining ordinary stars would be dominated by the smallest and longest-lived red dwarfs. Some could still be shining around the age in the title, while much of the matter around Voyager would exist in forms that produce little visible light. If the spacecraft were still inside a populated galactic remnant, the darkness would therefore contain more than the eye could see. Old white dwarfs, neutron stars, black holes, cold planets, asteroids, and other bodies could occupy the same system while contributing almost nothing to an ordinary view of the sky. A few faint red stars might remain visible at enormous distances, but the bright mixture of stellar colors familiar from Earth would belong to an early cosmic era. If Voyager had been ejected, the view could be emptier still. The local galactic remnant might appear as a distant concentration of faint light behind the spacecraft, while other major structures lie beyond horizons made increasingly difficult to reach or observe as the universe expands. The artifact could drift through a darkness where no nearby star illuminates its antenna, assuming an antenna still exists, and where the golden record receives almost no light from anything close enough to reveal its surface. That is one of the more unsettling possibilities, not because anything inside Voyager can feel isolation, but because the object was created in one of the most luminous periods of cosmic history. It left a planet under a bright sun, passed worlds lit by that same star, and entered interstellar space while the Milky Way still glowed with generations of active stars. 10 trillion years later, a surviving remnant could occupy a universe where most of those sources have become dark objects, and only the longest-lived stars preserve the old idea of a stellar sky. Yet, the location alone is not what makes Voyager interesting at that age. A natural asteroid could also wander through the same darkness, and a free-floating planet could survive for equally extraordinary periods. But Voyager would carry a history that began deliberately. Its trajectory started because humans built a machine, placed it on a rocket, guided it past Jupiter and Saturn, and used those encounters to send it onto a path that would never return to Earth. The golden record makes that origin visible in a way the dead instruments may not. If enough of the record survived, its diagrams and stored information would point back toward an environment that had vanished trillions of years earlier, preserving a description of oceans, animals, people, weather, music, and a solar system illuminated by a main sequence sun. The farther the universe moved away from that condition, the stranger and more valuable such a record would become as evidence of what once existed. In that sense, the final answer has two layers of uncertainty that cannot be removed. We do not know exactly what physical part of Voyager could survive, and we do not know the exact gravitational path that surviving material would follow. What physics allows us to say is broader but still powerful. If a recognizable remnant survives, it can continue moving for trillions of years, and its future belongs to the evolving gravitational environment of the galaxy rather than to a straight line drawn from Earth. By 10 trillion years, the question has changed from which star will Voyager pass to what kind of universe still contains it. That shift is important because no single star is likely to become its destination. Voyager was never aimed at a world where it could stop, and its silent journey has no planned arrival. Every stellar passage is temporary. Every orbit can be altered, and every new gravitational neighborhood becomes only another section of a path whose duration is limited mainly by the physical survival of the artifact. So where will Voyager 1 be in 10 trillion years? If something recognizable remains, it may still be wandering inside the ancient descendant of our local galactic system. It may be moving along its distant outskirts, or it may have been scattered into the far emptier space beyond. We cannot responsibly choose one exact location because 10 trillion years of galactic evolution separate us from the answer. What we can say is that it will not be where a simple straight-line calculation places it, and it will not be moving through the universe we see today. The sun that launched it will be gone as an ordinary star. The Milky Way will have changed beyond recognition, most familiar stars will have died, and the remaining stellar light will come from objects whose patience is measured in trillions of years. Voyager's location will belong to that future universe rather than to any map we could draw now. And perhaps that is the most fitting end for a spacecraft that never had a final destination. Voyager 1 was designed to visit planets, but after those encounters it became something much stranger. An object with nowhere specific to arrive, carrying the momentum of one brief technological civilization into a future that keeps changing around it. Its active mission may last only a tiny fraction of its physical journey. The last radio signal will fade while the universe is still young. Yet the silent artifact could continue through the death of the sun, the transformation of the galaxy, and the long decline of ordinary starlight, if chance allows it to survive. Almost everything that gave the spacecraft meaning would disappear before the motion itself necessarily ends. 10 trillion years from now, there may be no Earth waiting behind it, no familiar Milky Way surrounding it, and perhaps no complete spacecraft left to recognize. But somewhere in that ancient darkness, there could still be a fragment of metal, a damaged record, or the remains of an antenna whose journey began beside a small blue planet in 1977. And if any part of Voyager 1 is still drifting then, its exact location may be unknowable, but its presence would carry one simple fact across 10 trillion years. Something from Earth once found a way to leave home and keep going. Good night.